Hi everyone, this is Piyush Ranjan, a third year undergrad from the Department of Mechanical Engineering. We are making the group project of Mechanism System on the topic of Railway Ladder System. Our group members are Saurav Sekhar, Harsh Anand, Raghav Kasture, and me, Piyush Ranjan. Together we have worked on understanding, synthesizing, and simulating a mechanism that can be used as a deployable railway maintenance ladder system. In this problem statement slide, the goal of our project is to analyze its mechanism and then synthesize our own functional design. Basically, our task is to examine the transition between initial and extended state of this ladder and identify how the links are connected, what type of joints are used, and how motion is transmitted. And then create our own synthesized mechanism that replicates this motion and demonstrate it through SolidWorks and MATLAB. We are going to use double rocker mechanism in this project. So our next member Harsh Anand is going to carry on this project and to explain double rocker mechanism through MATLAB.
Hi, this is Harsh Anand, a third year UG from the mechanical department. I will be explaining the core mechanism of our railway ladder project. The entire system is built from a series of 4R mechanisms based on our analysis using the Grashof criteria, which for a double rocker holds true when the sum of the longest and the shortest links is greater than the sum of the other two links. We classify this linkage as a double rocker mechanism. We validated this mechanism using a two-part simulation approach. First, to prove this, we have created a simulation in MATLAB. This allowed us to model the kinematic equations, plot the exact motion of each link, and confirm the double rocker behavior was mathematically correct. Second, once the kinematics were proven in MATLAB, we built the 3D model in SolidWorks to validate the physical design. Now my teammate Saurabh will explain you about the simulation of the model.
Hi everyone, my name is Saurav Shekhar, a third year undergraduate student of the Department of Mechanical Engineering. I handle the simulation for our project. Our project focuses entirely on validating this design concept using digital simulation. Our primary objective for this simulation was kinematic validation. This answers the most fundamental question: does it move correctly? We needed to simulate and verify the complete deployment, the folding and retraction folding motion of the ladder mechanism. Our goal was to prove the geometry and linkages work as intended. With that goal in our mind, our first step was building the virtual model in SolidWorks to behave just like a real world object. We assembled all the components. Here the components are this is the plate for the ladder bridge where the passenger will stand. Other components are, this is the actuator part, this is the body for the motor, these are the links. For all the pivot points, we applied concentric mates to allow for correct rotation. Next, we used coincident mates to connect the linkages, ensuring they move together as one constrained motion. Finally, we grounded the base link part attached to the train. This created a fixed reference for all the motion. This is the fixed link which will be connected to the train component and as act our ground base. This will move like this. Now we have the model built. We are ready to test its motion using the motion study feature of SolidWorks. To drive this mechanism, we used a actuator motor to the primary shaft. This is the primary shaft. This part is the primary shaft. We have applied a motor in this actuator to move it. We will use motion study to see the animation. I set the speed 2.5x to see it correctly. We will now run the animation for the path verification, visually confirming the ladder deployed smoothly from run from its stored to extended position. As you can see, as the actuator moves, the ladder opens up. In summary, our simulation process successfully built a constrained virtual model and used it to validate the ladder's complete range of motion. Uh, we have confirmed how the ladder moves and verified critically that it does so correctly, with no geometric interference. This kinematic validation is the essential first step proving the fundamental concept of the mechanism is sound. Now I will pass the floor to my friend Raghav, who will enlighten you about the innovation that can be added to this model. Thank you.
Moving forward, we'd like to discuss several possible innovations that could further enhance our mechanism. Each idea is designed to tackle real-world challenges faced in railway operations and to make the passenger experience safer and more accessible. Over the next few slides, we'll go into the details about these possibilities, their motivation, their operation, and their potential impacts. Possible innovation number one, we could have hard die material end positions with piezo sensors. The first possibility centers around precise control of the mechanism's movement. In railway environments, reliable operation is critical. Errors in stopping positions can mean increased wear, delayed operations, or safety hazards. To address this, we could install hard die material at the extreme ends, both fully open and fully closed positions, acting as durable physical stops. Piezo sensors, known for their sensitivity to pressure and impact, would be placed on these stops. When the mechanism makes contact, the sensor detects the impact and signals the controller to halt the motor instantly. This approach could serve several benefits. Firstly, it provides a failsafe to prevent over travel if the motor does not stop in time, reducing the risk of mechanical damage. Secondly, it gives real-time feedback that helps reduce the load and stress on the motor, potentially extending its service life. Thirdly, with constant monitoring by the sensors, we can maintain a high level of safety, ensuring the ladder is in the correct position before passengers use it. Such a solution could reduce maintenance requirements and operational risks, especially in busy or unattended stations. Possible innovation number two, we could have a shaft key or radial gear locking mechanism. A second innovation addresses a common limitation with electric actuators, holding heavy loads over time. Typically, motors are great for motion, but inefficient for supporting static weight. Keeping a motor energized just to hold a position can cause unnecessary energy consumption and heat buildup. To overcome this, we could integrate a mechanical locking system. One method is the use of a shaft key, a small removable piece that slips into place between the shaft and its housing to lock rotation. Another option is a radial gear lock, where part of the gear system physically engages to block movement when not in active use. With this mechanism, once the ladder is fully developed, the motor can disengage and the lock would take over, bearing the static load efficiently, even with passengers on the steps. This prevents the motor from working continually to support the load, reducing energy costs and increasing the longevity of the motor. For maintenance crews and railway operators, such a lock means less frequent servicing and greater system reliability. It's also an added safety feature. Mechanical locks are less prone to failure than electrical holding systems, especially under unexpected loads or power interruptions. Implementing this innovation could help railways run more efficiently and safely on high traffic routes. Possible innovation number three, we could have proximity sensors and linear actuation for platform positioning. Platforms in India and around the world are rarely uniform in height. Trains might stop at stations where platforms vary by several centimeters or more. To guarantee optimal passenger comfort and safety, we consider the integration of proximity sensors like ultrasonic or infrared systems beneath the ladder. These sensors would continuously measure the gap between the lowest step and the platform as the train pulls it. Based on this sensor data, a linear actuator can then extend or retract the ladder support arm to match the exact platform height. This adaptation would provide several advantages. Boarding and exiting the train becomes smoother for all passengers, especially the elderly and those carrying luggage. For operators, there's less risk of steps being too high or low, preventing accidents. Moreover, automation here minimizes human intervention. Operators simply initiate the ladder's deployment and the system does the rest, using real-time feedback or deliver precise adjustment every time. Such a feature could make the system suitable for deployment on a wide range of rolling stock and platform configurations, and could even be expanded in the future with additional sensors for crowd monitoring or other platform features. Possible innovation number four, we could have an inclined plane mechanism for wheelchair access. The final innovation we want to highlight deals with inclusivity. Today, accessibility is a legal and ethical requirement for public transport. Many train ladders don't accommodate wheelchair bound or mobility impaired passengers, creating a barrier to travel. Our possible solution uses an adaptable mechanism. Using carefully designed linkages, these steps can be reconfigured to form a continuous inclined plane, a ramp. With a simple actuator movement, the ladder transforms from a staircase to a smooth ramp. This would mean that wheelchair users or people with strollers and heavy luggage could board independently, without station staff needing to deploy separate equipment or ramps. This benefits these benefits extend beyond legal compliance. Such a mechanism puts all passengers on equal footing, fostering independence and dignity for everyone. Additionally, this innovation demonstrates our commitment to universal design, making public transport accessible and comfortable for all users. With further refinement, the mechanism could be adapted to accommodate different platform widths or gradients, making it a versatile solution for the future of urban and long distance railways. Thank you.